In electrical engineering, there are equations with real number coefficients, but whose solutions are not real numbers. These equations are integral part of the study of electricity. Hi, my name is Tom Atwater, and in today's lesson, we will be investigating complex numbers and the fundamental theorem of algebra. Let's start off by taking a look at a graph. Here I have the graph of f of x equals, and you may have guessed that I'm going to start with x squared since it is a parabola, plus 2x plus 5. And what's interesting about this graph for us is that it does not have any real zeros. That is to say, it doesn't cross the x-axis anywhere. However, it is a polynomial of degree 2, x squared, which means we'd expect it to have two zeros. In other words, two solutions to the equation where f of x is equal to 0. Well, let's use the quadratic formula, and if we were to do that, we would find that in fact it does have two solutions. One solution is x equals -1 plus 2i. And it has a second solution, x equals -1 minus 2i. So in fact, we do get two solutions to that quadratic equation, but they are within the set of complex numbers. Let's formalize this idea that we just did into two theorems. First, we have the fundamental theorem of algebra. A polynomial function of degree n has n complex zeros, real and non-real. Some of these zeros may in fact be repeated. The second theorem I want to look at is called the linear factorization theorem. And it says if f of x is a polynomial function of degree n greater than 0, so it has a positive degree, then f of x has precisely n linear factors. And f of x would be equal to a times the quantity x minus z sub 1 all the way through the quantity x minus z sub n. And they are where a, of course, is the leading coefficient of f of x, and z1, z sub 1, z sub 2, and z sub n are the complex zeros of f of x. The z sub i's are not necessarily distinct numbers. Some of them may in fact be repeated. Well, as we've already observed, if k is a complex zero of a polynomial function, then k is not an x-intercept. However, we can make the following statement about the fundamental polynomial connections in the complex case. The following statements about a polynomial function f are equivalent if k is a complex number. Number one, x is equal to k is a solution or a root of the equation f of x equals 0. Number two, k is a zero of the function f. And number three, x equals k is a factor of f of x. So those are all equivalent statements to each other if k is a complex number. Let's work a few examples of this idea. Write the following polynomial function in standard form and identify the zeros of the function and the x-intercepts of its graph. The first one that I want to look at is f of x equals x minus 2 times x plus 2i. To put this in standard form, we need to expand the right-hand side. So this would be f of x is equal to x times x gives me x squared. X times 2i gives me 2ix. Then minus 2i times x gives me negative or minus 2ix. And then negative 2i times positive 2i is minus 4i squared. Now, the middle two terms add up to 0. So what we get is f of x equals x squared. And then, remember that I squared is negative 1. So we're multiplying negative 4 times negative 1. So this would be plus 4. So we have f of x equals x squared plus 4. We can see from the original problem that the solutions to the equation are x equals 2i or negative 2i. Now, since they are complex numbers, that is, they're not real numbers, there are no x-intercepts for this particular equation. Well, let's go on to part B. Part B, f of x is equal to the quantity x minus 5 times the quantity x minus the square root of 2i times the quantity x plus the square root of 2i. We need to multiply all of these together in order to put this into standard form. So let's take a look at the last two, though, because those actually multiply together nicely in the sense of that things cancel out, right? Because it's really the difference of two squares. So we would get our x squared, but then the middle term, the negative radical 2ix, will add up to 0 with the second middle term, which is positive, the value square root of 2ix. And then at the end, when we multiply negative square root of 2i times positive square root of 2i, that would be negative 2i squared, but I squared is negative 1. So negative 2 times negative 1 gives us a positive 2. So what we need to do then is multiply x minus 5 times x squared plus 2. All right, so that gives us f of x is equal to x times x squared gives me x cubed. X times 2 is going to give me plus 2x, but I'm going to put it over here because I recognize that when I come back and multiply the 5 into this set of parentheses, I get negative 5x squared. And that way I've put it in descending order. And then finally, the minus 5 times the 2 gives me negative 10. So that's my function in standard form. Well, what about the zeros of this function? The zeros are, of course, from here, x equals 5. From the first factor, what about this one? This would give us plus the square root of 2i. And the third factor would give us the negative square root of 2i. In this particular case, we know that x equals 5 gives us an x-intercept, whereas these numbers, which are imaginary, do not yield an x-intercept. All right, let's go on to part C. Part C says f of x is equal to x minus 3 times x minus 3 times x minus I times x plus I. So let's deal with expanding this out. If we start with the x minus 3 times x minus 3, of course, that's x minus 3 squared. So it's a binomial squared, which leads us to x squared minus 6x plus 9, a perfect square trinomial. Then we can use what we've already seen before. When we're multiplying a complex number by its conjugate, we get the first term squared, so that's x squared, plus the last term, or when we multiply, I guess I should say, it's negative I times I is negative I squared, which gives me a plus 1 because I squared itself is negative 1. All right, as you can see, if we were to take the time to multiply this out, we would end up with a fourth degree polynomial function. So I'm just going to go right to my final answer, which is f of x is equal to x to the fourth minus 6x cubed plus 10x squared minus 6x and then plus 9. So that's our quartic equation in standard form. What about the zeros? We can see that the zeros are 3, right? And it happens twice. It's a repeated factor. We also get, so let me write these down. We get 3, and then over here we get plus I, and we get minus I. And in this particular case, 3 is in fact an x-intercept. And it has multiplicity of 2, because it's a repeated factor, and an even number of times, twice in fact, and therefore it doesn't cross the x-axis. Well, next we are going to explore something called the complex conjugate zeros. And that is, suppose that f of x is a polynomial function with real coefficients. If a and b are real numbers, where b does not equal 0, and a plus bi is a 0 of f of x, then its complex conjugate, a minus bi, is also a 0 of f of x. Let's try an example where we use this theorem. We have we want to write a polynomial function of minimum degree in standard form with real coefficients whose zeros are -3, 4, and 2 minus I. Okay, well, realize, first of all, that by the complex conjugate zeros that we just looked at, if 2 minus I is a factor, is a 0 of the polynomial, that means that 2 plus I is also going to be a 0 of the polynomial. So let's take a look at the actual equation or the function that we would come up with. These are the zeros we were given, but we also have already said that that means 2 plus I is a 0. So when we begin to build the function, we can take each of these zeros and subtract them from x to give us each factor. So this would be x minus a -3. In other words, x plus 3. The next factor would be x minus 4. And then we have x minus, in parentheses, 2 minus I. Then we would have x minus, and in parentheses, 2 plus I. I'm not going to take the time to multiply all of this out, but I do want to show you something that mathematicians often do when they're multiplying these types of factors. And that is, they actually rearrange these by distributing the minus sign, and this one becomes x minus 2 plus I. And I put space there, which I'll come back to in a moment. This one, when we distribute it, becomes x minus 2 minus I. And what I want to point out is that if I put parentheses around this x minus 2 and this x minus 2, you can see that this is like a plus b times a minus b. In other words, we have the difference of two squares. I'll let you multiply that out. The result you should get is this: f of x equals x to the 4th power minus 5x cubed minus 3x squared plus 43x and then minus 60. So that would be the function in standard form that has those zeros. Let's work a problem going the other way, which is let's find the zeros of a function. Find all the zeros of f of x is equal to x to the 5th minus 3x to the 4th minus 5x cubed plus 5x squared minus 6x plus 8. And write f of x in its linear factorization. Well, we can use some of the materials that we've learned earlier. Let's start by graphing this so that the grapher can help us find the real roots. Here's the graph. So it appears to us from the graph that -2, +1, and then +4 are real roots to this particular equation. Well, that's helpful because we have a starting point. So let's start with those possibilities. We know that we have those three, -2, 1, and 4 as real roots. Now, if we were to perform synthetic division using each of these roots, we verify that they are zeros, and once we do that, we would be left with a quadratic x squared plus 1. Now, what that means is, besides the three real roots that we have of -2, the x-intercepts of -2, 1, and 4, we also have two complex roots. Because when we set this equal to 0, we will get that x is plus or minus I. So we can now write the linear factorization, and it would be f of x equals x plus 2 times x minus 1 times x minus 4 times x plus I times x minus I. Well, that was great because it really combined together a lot of different ideas that lead us to be able to write that linear factorization. Now, we can use synthetic division with complex numbers, which obviously will help us to find complex zeros. Let's try an example, and the example is this. The complex number z equals 1 minus 2i is a zero of f of x equals 4x to the fourth plus 17x squared plus 14x plus 65. Find the remaining zeros of f of x and write it in its linear factorization. Alrighty, so this was our original equation, our original function, and we're going to perform synthetic division using as the divisor 1 minus 2i. So let's set that up now. We have 1 minus 2i, and we're going to divide that synthetically. So I need to take down the coefficients of my terms. And of course, there's no x cubed, so we have to put 0 in its place. We have 17 for the x squared, 14 for the x, and 65 as the constant term. All right, so now we bring down the 4. We multiply 4 times 1 minus 2i. That gives me 4 minus 8i. I add that together with the 0, and of course, that's 4 minus 8i. Now I need to multiply 1 minus 2i times 4 minus 8i. That gives me negative 12 minus 16i. Then I need to bring this down, add them together. That's going to give me 17, and the minus 12 is 5 minus the 16i. I multiply that times the 1 minus 2i, and that gives me negative 27 minus 26i. So then I combine that with the 14, and that's negative 13 minus 26i. When I multiply this times 1 minus 2i, and I combine everything together, I end up with negative 65, which when I add it, of course, gives us 0. Now, that's what we expected to find, of course, because we knew that 1 minus 2i was a 0 of the function. So getting 0 as our last element is exactly what we would expect. Now, the next step would be to divide synthetically this set of terms by 1 plus 2i. Now, I'm going to leave that actual division process to you, but what I will do is write down what that yields in terms of the final result. But you would actually have to fill in, of course, you'd bring the 4 down, and then you'd have to fill in each of these positions. Once again, you'd expect it to leave a 0 as the last term, and in fact it does. Let me show you what it would give you. It gives you 4, and then 8, and I'll do the 4 over again, so it's all the same color. We have 4, 8, then 13, and as expected, that would give us 0. So what does that mean? It means that we have a quadratic, which would be 4x squared plus 8x plus the 13. And that is the part where we'd have to use the quadratic formula. And if we do that, we get the other two complex zeros. And those complex zeros would be -1 plus or minus 3/2 I. So with that, I can now write out the linear factorization. So the way it works would be that f of x would be equal to, of course, the leading coefficient of 4, and then I would have times x minus the first one of 1 minus 2i. Then I would have x minus 1 plus 2i. And I'm going to write it down below, but if I had enough space, I would continue. But my next factor would be x minus, and I'm going to work with the complex numbers that we got from the quadratic. That would be -1 plus 3/2 I. And my fourth factor would be x minus, parentheses, -1 minus 3/2 I. And that would be the linear factorization of the original problem, f of x. In this example, we had a quadratic equation which had real coefficients, but no real zeros. There's a name for this. It's called irreducible over the reals. In other words, if we require that the factors of a polynomial with real coefficients, or that it has real coefficients, then the factorization can be accomplished with linear factors and irreducible quadratic factors, because that's what I have here. Those are real coefficients, but it's irreducible. Let's actually formalize this idea. We'll take a look at factors of a polynomial with real coefficients. Every polynomial function with real coefficients can be written as a product of linear factors and irreducible quadratic factors, each with real coefficients. We're going to take a look at another helpful idea that follows up from here, and that is polynomial functions of odd degree. Every polynomial function of odd degree with real coefficients has at least one real zero. The best way to see this is to take a look at an example. Write f of x equals 3x to the 5th minus 2x to the 4th plus 6x cubed minus 4x squared minus 24x plus 16 as a product of linear and irreducible quadratic factors, each with real coefficients. So to start this process, we need to find one of the zeros. And from the rational zeros theorem, we know that a real zero comes from taking all of the factors of 16 and dividing them by the factors of 3. And we take both the positive and negative. Well, I obviously worked out this problem ahead of time, and I know that one of the possible factors is 2/3. And if we take a look at the graph, we can see that, in fact, 2/3 is an x-intercept, which means that it is a 0 of the particular function. So what we do now is we use synthetic division of the 2/3 into that original function. And when we do that, we come up with the following result. We divide by the x equals 2/3, and it's going to, and I'll leave the synthetic division up to you, but what it would leave us with is 3x to the 4th power plus 6x squared, then minus 24. And what I'm going to do, first of all, you should notice that there is a common factor of 3, which I'm going to factor out to the outside, and that's going to leave me x to the 4th plus 2x squared minus 8. And I'll come back to the 3 and the 2/3 in a moment, so let's continue dealing with this. When we factor this, because it does actually factor, we get x squared minus 2 times x squared plus 4. All right, now let's go back to the 2/3. That, of course, would give us a factor of x minus 2/3. And what I'm going to do now is take the 3 that we factored out and distribute it into this factor so that I get 3x minus 2. And what you can see now is we are left with a linear factor and 2 irreducible quadratics. Actually, I just realized this, although I said it was irreducible, that's reducible. And so we need to take this one step further. So I'm going to put in my f of x, and that equals 3x minus 2 as the first factor. And then I can write x squared minus 2 as x plus the square root of 2 times x minus the square root of 2. And those, of course, are real numbers, non-complex numbers, I should say, non-imaginary. However, I was correct when I said that x squared plus 4 is irreducible, and now that's as far as we can go. Each of these factors has real coefficients, and so that would be the solution to that particular f of x. Well, now it's time for you to try a problem. So what I have for you is write the function f of x equals x cubed minus x squared minus x minus 2 as a product of linear and irreducible quadratic factors, each with real coefficients. Now pause the video to work on this problem, and when you are finished, restart the video to check your solution. Welcome back. Let's find out how you did. Of course, by the rational zeros theorem, we know that we take the constant term and the ratio of it and the coefficient of the x cubed term, and that gives us the possible ones. But of course, rather than trying all of those and seeing what works, we can put it into the grapher and check out. And we can see from the grapher that in all likelihood, 2 is an intercept, and therefore 2 is a 0 of that function. So you can start off knowing that x minus 2 is one of the linear factors of that function. So let's move to a blank screen and we'll work it out. So we're saying already that we know that x minus 2 is one of the factors. And we could show that if you went through the using synthetic division, you'd end up with a 0 at the end, which is what we would expect. And what we're left with is x squared plus x plus 1. And that's actually is irreducible over the reals. So our answer is in fact x minus 2 times x squared plus x plus 1. And that is equal to the original f of x. And note that we have one real 0 as we expect. X equals 2. All right, great job on that. Now in this lesson, we explored complex zeros and the fundamental theorem of algebra. Be sure to work the exercises that your teacher assigns, and we'll see you next time.